Okay, so we're going to start section 4.8. Come on, erase. Why is my thing not erasing? We'll do it the long way here. Oh, there it goes. Oh, my pen is not responding here. There we go. All right, 4.8. I just did it again. 4.7. L'Hopital's rule. And what this does is this provides us another way to compute limits. And this is also going to mark the last section that's on the next exam. So this is going to be the end of the material that's going to be on exam 3. Now, before we get into this, I want to remind you that we're going to have a quiz on Wednesday. The quiz on Wednesday is going to cover sections 4.4 and 4.5. All right, so let's write L'Hopital's rule down here. So the theorem here. Suppose f and g are differentiable on an open interval I containing A with g prime at A not equaling 0. If the limit as x approaches A of f at x equals the limit as x approaches A of g at x equals 0, then the limit, I'm sorry, not, this shouldn't be infinity here, x approaches A. They should both be limit as x approaches A. The limit as x approaches A of f at x divided by g at x is equal to the limit as x approaches A of f prime at x over g prime at x. Now, I know this looks a little confusing here. What I really like to think about this, and we're going to talk about this more because when we pursue this section a little bit more, we're going to be talking about the forms. Basically, what we're saying is we have some function, I'll call it h at x equals f at x over g at x. And what we're saying here is that you can think of it as that f at A over g at A gives you 0 over 0. Which, remember, back at the beginning of the semester, we said if you got 0 over 0, then there was more simplification that you could do. Well, that's not always the case, and we'll see why that's not always the case here in a second. But we can figure out what these limits are going to be. So what we're saying is then if we get that case where we have f at A over g at A being equal to 0 over 0, then the limit as x approaches A of h at x, which is the limit as x approaches A of f at x over g at x, is equal to the limit as x approaches A of f prime at x over g prime at x. So I'm going to do this an example here where we already know what the answer is without doing this kind of weird L'Hopital's rule thing, and then we'll apply L'Hopital's rule to it. So let's look at an example here. So example, let's look at the limit as x approaches 3 of x minus 3 over x squared minus 9. Now, if I plug 3 in, I get 0 over 0. Now, this is one that we can already do with techniques that we learned back in chapter 2. Because what we can do is say, oh, look, the denominator factors, and you get the limit as x approaches 3 of x minus 3 over x minus 3 times x plus 3. And then we say, oh, wait, if you can reduce here, the limits stay the same, so I can cancel out those x minus 3's, and then this is just the limit as x approaches 3 of 1 over x plus 3. Great, so we get that, and then we would say, oh, well, now I can just plug in the 3, so this is be limit as 1, not limit, this would be equal to 1 over 3 plus 3, which is 1 over 6. Now we're going to do this exact same problem using L'Hopital's rule to illustrate how we use L'Hopital's rule. So what we have here is we're going to have exact same problem, limit as x approaches 3 of x minus 3 over x squared minus 9. And now what I'm going to do here off to the side, I'm going to say that this is in the form 0 over 0. And the reason I'm going to say form 0 over 0 is when we start looking into this section more, there's going to be different forms, and we'll apply different techniques for different forms. So this form is 0 over 0, so I can directly apply L'Hopital's rule. And if I directly apply L'Hopital's rule, that's saying that this is equal to the limit as x approaches 3. Now I take the derivative. Well, what's the derivative of x minus 3? This should be very easy for us all. This is, of course, just 1. Derivative of x squared minus 9, well, that should be easy as well. That is 2x. And then, well, this we can simply just plug in 3 in this case. 1 over 2 times 3, which is 1 over 6. So we get the exact same limit. This case we used L'Hopital's rule. In the first case we used the factoring method. Now, we can use this for other ones as well. Remember, back when we were proving derivatives of trig functions, I told you that the limit as x approaches 0 of the sine of x over x, I told you this was equal to 1. But we're going to use L'Hopital's rule to verify this. Well, what do we have here? Well, first off, if we're looking at the limit as x approaches 0 of sine x over x, you have to make sure you're in the proper form, because we have to be in the form of 0 over 0. So, well, we should look at what's the sine of 0, and of course this is over 0, so that would be 0 over 0, which is our form, because the sine of 0 is 0, of course. Alright, so I can use L'Hopital's rule. So if I can use L'Hopital's rule, that means that this is equal to the limit as x approaches 0 of the derivative of each thing. So the derivative of the sine function is simply the cosine function. Derivative of x is simply just 1. So this would give me the cosine of 0 over 1, which is 1. Okay, we're going to do one more example here, and then we're going to wrap this up. And this is just scratching the surface of this section. There's a lot more we need to talk about in this section. So sometimes you need to use L'Hopital's rule more than once. Well, what do I mean by that? Well, let's look at an example here. So I've got the limit as x approaches 0 of e to the x minus 1 over x squared. So let's first check that we're in the right form. So if I do e to the 0 minus 1 over 0 squared, this would be 1 minus 1 over 0, which is 0 over 0 form. Okay, because you have to be in the 0 over 0 form in order for this to work. So then this is limit as x approaches 0. Now we take a derivative. Derivative of e to the x is e to the x. Derivative of negative x is minus 1. Derivative of negative 1 is 0, divided by 2x. So at this point we want to try and plug the numbers in again, but if I do that I have e to the 0 minus 1 over 2 times 0, which would be 1 minus 1 over 0, which is still 0 over 0 form. Well, it's not a big deal that it's 0 over 0 still, because all I do is apply L'Hopital's rule again. So this is equal to the limit as x goes to 0. Well, derivative of e to the x is e to the x. Derivative of 2x is 2. And then if I plug 0 in, I get e to the 0 over 2, which is 1/2. So to kind of make sure we understand what we just did here, we have that the limit as x approaches 0 of e to the x minus 1 over x squared is equal to 1/2. And we did that using L'Hopital's rule. Now, as I said, this is just scratching the surface of it. There's going to be more forms that we're going to look at. Some of the other forms we're going to look at is r infinity over infinity, which it turns out infinity over infinity works just the same as 0 over 0, so that's convenient. Nothing new about that. There's infinity times 0, which is, we'll have to do something with that. And then there's like 1 to the infinity. There is 0 to the 0, and infinity to the 0. And these all, these other three take a special technique. And there's one that we may talk about. I don't necessarily talk about it all the time, but if you have infinity minus infinity. Infinity minus infinity is not necessarily 0, because infinity again is just used to represent that numbers go on forever. So you can't say that, well, a number that goes on forever minus another number that goes on forever is 0. We don't know what that's going to be. All right, but that's where we'll end today. So reminder of a quiz on Wednesday over sections 4.4 and 4.5. You will be allowed to work in groups still.